So my slides are up. I guess that means I'm starting. There's a couple people still filtering in. Feel free to come on in and sit down. We're going to be talking about microservices with ASP.NET Core today, and a couple more specific things that I'll get into in a little bit. So I'm Ryan Nowak. I'm a framework developer and architect working on ASP.NET Core. You could say that I probably have a particular focus on things like MVC, routing, Blazor, Razor Engine, language, and tooling. All the things that people use to write applications. I'm really interested in how people program things, how people use frameworks, and how to make people more productive. I'm also really interested in performance. You can find me on Twitter if you want, and you'll be able to find all my materials and demos online later. My last slide will have a more comprehensive set of links to all of the things. So today we're going to be talking about microservices, and I'm going to be talking about microservices in the context of ASP.NET Core, .NET Core, and Kubernetes. And so what is Kubernetes? How would you use ASP.NET Core and Kubernetes? And what are some things that we can learn about performance of .NET Core and ASP.NET Core in containers? That's what's on our agenda for today. So you might be asking, or you might be reading Twitter, or reading somebody's latest hot take or latest meme, what are microservices? Are they the definitive solution to all applications? Must you do everything in microservices today? Are they just very small services? Do you just write less code? Do you use different frameworks or different technologies? These are all the kinds of things you might hear about microservices if you haven't actually tried building microservices applications. And the answer I'll give to all those questions is like, well, no, but sometimes kinda. Like, you might write less code. You might use different frameworks and tools. You might design things differently if you have multiple services. They might be the solution to your problem. They might cause you problems. So there's some truth in all the things that we hear about microservices. There's some aspect of all of those statements that are true for somebody somewhere at some time. And only you and your company or your organization or your team can really decide what's right. So there's a lot of banter on Twitter today. I think maybe the last week in the developer community, at least among some of the people that I follow and messages that I see around, people's hot takes or rants about, I wish we didn't have to do microservices for everything, or we don't have to do microservices for everything. And the truth is that I'm kind of like you. Like, I'm a framework developer. I'm a tools developer. I help people program. I work on the framework. I fix bugs. I cause bugs. I'm not an application development consultant or a really like in the trenches, like application deployment kind of person. I don't have that experience. So the things that I do learn, I hear from blog posts, I hear from talking to customers, I hear from interviewing people or getting their feedback about what things work and work well for them and don't work well. If I sort of summed up what I do know and what I do hear from people, it's kind of that doing microservices deployment or doing microservices development or migrations might make sense for you if you're going to get something out of it. If you're going to get the ability to deploy and develop things separately, if you're going to get the ability to evolve parts of your code base or to work more productively as an organization, you might want to consider that. If you don't feel like you could get those benefits out of breaking up a larger application into multiple services, let's say maybe you don't have good discipline around using source control and CI and having deployment pipelines and having good ways to do code reviews and check things in and deploy them to production in your organization, this is probably not the silver bullet that you're looking for. So I'm not a salesman. Presumably you're here because you wanted to hear some information. I'm not going to try and explain to you whether or not that's the right choice. Hopefully you can figure that out for yourself. You know your business better than I do. As a framework developer, how I kind of tend to think about microservices is they're not that different from not microservices. I mean, many of you in the audience, I'm sure, have written applications before where you have a front end and a back end and then maybe another back end, right? Is that microservices? Kinda. It's all just backend to me. The difference between general backend development and microservices development is that there is a set of problems that kind of just get like cranked up, right? Because you've got way more things that are going to deploy and version differently. And so there's a set of problems that are going to get cranked up that you're going to have to invest more in, and you're going to have to learn more about solutions to those kinds of problems if you want to be successful. And that's what we're going to spend our time sort of focusing on. Whether or not you're doing microservice-y kinds of stuff, though, as a backend developer, you probably still have those problems, and you probably still care about a lot of this kind of information, even if you're not really reaching for a microservices kind of deployment. So we are spoiled for choice in the world of how to deploy microservices, or where to run your code. Like, where are you ultimately publishing to, right? I tried to be egalitarian and fair with whose logo that I put on the slide, despite the fact that I work for one of these cloud providers. I won't say which one, but you can probably guess. I tried to be fair and not make anybody's icon much larger than anybody else's. But you've got a lot of places where you can deploy and you can run code today. You've really got a lot of options. And how you deploy, where you choose to deploy, how you want to get billed is actually probably going to have a pretty big effect on how you write code. I would encourage anybody to think about, like, as I'm giving you information, and I'm going to be focusing on one area in particular, but what are the consequences of the choices you make about how you deploy code? And do they help you? Do they hurt you? What are the things that you need to do to compensate for the weaknesses in that platform, or the things that that platform simplifies for you? How do they help you? Because we're going to be talking today about Kubernetes. You probably hear a lot about Kubernetes these days, and there are a couple talks about Kubernetes at this conference. I think what some of us developer and developer tools kinds of people really like about Kubernetes is most of all the fact that Kubernetes is probably the most complicated, sophisticated, and powerful deployment environment you could have. It's like an operating system for deployments. And so as a result, you could pretty much program Kubernetes to do anything you want. Like, if you want to write a piece of code that runs in your Kubernetes cluster that looks at all the deployments coming in and rejects them unless they're annotated a certain way. Like, people have built Kubernetes infrastructure and projects to do that. You might not even have to build it yourself, right? If you want to audit all the deployments in your topology, or all the things that people are doing, like, Kubernetes is basically just a big REST API. So, like, you can write that code, and it's pretty easy to do, and it's pretty fun to extend Kubernetes. There's a lot of great projects out there today that will help you with those kinds of things, and they're all pretty neutral about what type of technology you're using. Kubernetes really doesn't care. It's primarily based on Docker or OCI container images, and it doesn't care what technology stack you're using. It's very egalitarian in that way. And the community of developers and developer docs around Kubernetes don't really speak to, like, well, you've got to be a Node developer to use this. You've got to be a Java developer to use this. All the technology that's out there is for everybody, which is pretty awesome. The other great thing about Kubernetes is you can really run Kubernetes kind of anywhere. So all the major cloud providers have a Kubernetes offering if you want to go that route, if you want to pay for a managed Kubernetes system. Likewise, you can run Kubernetes on your own. You can deploy your own Kubernetes setup, and you could administrate it on your own hardware or VMs if that's something you want to do. You really have the choice no matter where you are and where you're doing if you wanted to do this. Lastly, I think the thing that's most exciting about Kubernetes as a platform, for those of us that work on platforms and work on developer tools, is that it's kind of like an operating system. Like, a lot of the leaders in the Kubernetes community are saying things today like the current wave of Kubernetes usage is like assembly language, right? We expect Kubernetes as a platform to grow and evolve and support more high-level, less complicated application models in the future. And so it's kind of worth learning about some of the things that it does today from the point of view of understanding that better. If this seems complicated to you, it probably will be simplified in a few years, which might help you out, might be something that you're looking for. Oops. So I'm going to do a quick demo to introduce a couple things. And hopefully this is at least a little bit interesting, or sort of gives you the impression of some of the power that you have with Kubernetes. Now, I'm going to be doing a lot of things at the command line here. I hope that's okay. Kubernetes is sort of a command line focused tool, or a command line first tool. I'm going to be deploying a very simple .NET Core application. And this is the code right here. And the only thing that I'm really doing in this code is I'm writing hello world, and I'm writing what IP I'm listening on and what hostname I'm listening on. And then the way that I deploy this application is with this YAML manifest. I want everybody, if you want to, like, take a moment and react in whatever way you think is appropriate to the fact that I'm showing you a YAML file. Like, if you want to sigh, remember you're being recorded, but like, if you want to react to the fact that there's YAML here, go ahead. I've been working with this for a while, and I can't I can't really imagine another tool that's better for the job, which I guess sounds a little bit weird, but I can't imagine this being JSON or something like that. Like I think it might actually be harder if it weren't YAML. So let me go ahead and deploy this. Now I'm gonna be running some scripts so that you don't have to watch me fumble around and fail to type. But you will see that I'm printing to the console what I'm doing there. And so what's going on here is I've taken that manifest and I've deployed it to the cluster with this command. If we go back and we look at this manifest real quick, there's two objects here. This is what that dash 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 means. It means I've got like two separate declarations in this file. I've got a deployment object and I've got a service object, and they've all just got lots of stuff. Like this is really verbose and confusing, and I'm gonna try and break down the things that matter, because as an application developer, a lot of this does not matter to you and will not really matter to you. A lot of this is boilerplate code. So every object in Kubernetes has got a metadata section. And in the metadata, you're gonna find a name. You're gonna find labels. Labels are key value pairs, but they're for humans. You may find annotations. Annotations are key value pairs, but they're for infrastructure and for machines. Not gonna say too much more about that other than they're ways of identifying this object. The thing that really matters here is the spec. So a deployment object represents, in Kubernetes, a long-lived, like server kind of thing, right? So I'm gonna have 3 replicas. You can ignore all this stuff. And each one of those is gonna have one container, and it's gonna point to this image. Now, I've already pushed this image to my Docker Hub, so this image is already sitting out there. And I'm gonna expose port 80. And then in addition to that, I'm gonna have a service. And the service is of type load balancer of port 80. So what's going on with this service declaration is a service basically identifies in Kubernetes, here's a thing that you can talk to. If you're inside the cluster, or in this case, because I made it of type load balancer, if you're outside the cluster, here's a thing that you can talk to that is gonna be running here. A deployment alone doesn't make it easy to find and talk to this deployment. The service is what does that. It's gonna create DNS records. I have exposed this publicly so that we can talk to it, and using type load balancer is kind of like the dumbest way to do that, but it's great for demos, so I'm doing that. I'm doing it that way. And then over here, we're now ready to explain what the output of this command is. So a pod you can think of as like an instance of my deployment. So I went ahead and I created this, and I used the watch command so you could see all the things that happen. And gradually 3 instances of my deployment got created. That's what you see here. And we ended up with 3 separate instances, 3 separate pods, 3 separate names that are all running. So I'm gonna exit out of that. And my next step here, we're just gonna run a little shell script. I'm getting the public IP of that service that I just deployed, and then I'm sort of pinging it repeatedly. And you can see that I'm getting responses from different endpoints here. I'm getting responses from different IP addresses and different host names, because there are 3 copies of this service running. So you see I get response from 33, 48, and I think I saw a 38 in there. I've got 3 copies of this thing running. The next thing that I can do is I can upgrade this deployment. So I've got another copy of my app. And my other app is gonna output some different text. If I come to my startup here, this one says, by the way, this is the 2nd version, and other than that, it's pretty similar. The only thing that's different about this is I've added a health check to it. Now, health checks has been around in ASP.NET Core for the last couple releases, and you don't necessarily need a health checks package or health checks infrastructure to do health checks, but we find that it's kind of helpful for a variety of reasons. What I've changed about this deployment and the way I'm gonna update this is I've told Kubernetes, I want you to check that this thing is ready before you send any traffic to it. That's what this readiness probe is. And I have tweaked these numbers to be slow so that it's gonna sort of take a little bit of time to know that this thing is ready. And the whole reason I'm doing that is just for demo purposes, so you can see what I'm about to show you. And then additionally, what I've customized here, I've updated this to the 2nd image of the app. But the other thing that I've customized here is I've changed the deployment strategy to rolling update. And I've basically configured this to do something kind of special and kind of complicated to explain, but easy to understand why you'd want to do it. So what this is going to do is when I update this app, it's going to create 1 copy of the new app, wait for that to be ready, and then delete 1 copy of the old app, and so on. So there's never gonna be fewer than 3 copies of my app running, and it's going to gradually arrive at the new app being the only one running. So I'm gonna go ahead and start that. This is deploying the new copy of the YAML file, and that's running. And then over here in another terminal, I'm gonna run that same command that we ran to ping it and display the output. And if I did this right, we should see that gradually this is gonna switch So you can see that we haven't started bringing in the new copies of the service yet, and there it went. So you should start to see now, we're going to get some mixed responses here. We're going to start seeing some responses in just a few seconds from our new app as they come online. And it's taking its time. So it says we have 2 up to date, we have 3 ready and 3 available. So there, we started to see some traffic from the second version. And you can see that they're sort of intermingling. We're seeing mixed traffic from the first version and the second version, because both of them are running in production at the same time. And then as these new instances come online, it's going to sort of taper off all the old ones until we get to the state where everything is transitioned onto the new system. So this is pretty sophisticated, and I was able to do that with just a couple lines of YAML. I remember when I was 16 years old and I was working at an internet service provider in Toledo, Ohio, and we would literally like change the DNS record and then like unplug and replug like different computers to do this kind of thing, to try to do a migration with no downtime. But we've actually done a migration to an upgrade to a new app with no downtime in a totally automated way with just like YAML that we can source control. So I'm going to go ahead and clear this up, because we don't need that anymore, and get ready for my next thing. Okay. So that's kind of an intro of some of the things that you can do with Kubernetes that are pretty powerful. So you might be asking at this point in the presentation, like, I'm demoing this on Mac, I'm doing all this at the command line, I'm a Windows developer, can I do this with Windows? So I had actually planned on showing a mix of Windows and Mac to try and hammer that point home, but something bad happened to me. I want to say first that this was not my fault, it was an accident. So I kind of smashed my computer on Thursday before I came here, which is kind of unfortunate. But if you don't physically break your computer, Windows works pretty well for doing Kubernetes and for doing Docker. WSL2 makes it work really well. And I've been using that pretty happily on my like Windows workstation at work, as well as my personal Mac, which I'm using for this presentation. If you're not a command line sort of person, VS Code has got really excellent tools for Kubernetes, at least as far as being able to visualize and see what's going on. So if you're more of a command line, if you're more of a GUI type of person and you want to say, right click, give me the logs of this thing, or right click, you know, tell me what's going on with this thing, Visual Studio Code has got really excellent UI for doing Kubernetes. So as developers, there's lots to like about this. First of all, the main thing, like all of these small decisions, like the number of replicas or how we're deploying, how we're rolling out, how we're doing health checks, they're not things that you configure in some UI somewhere. They're things that can all be source controlled. So like all the details of your deployment of your operations that matter, you can source control in a way that is going to help you and is going to work with the way that you flow data and the way that you do check-ins and things today. And lastly, it's a big REST API. So like it has a command line tool that lets you query stuff and write your own kind of queries to find out data or find out what's going on. You can drop to a lower level and write your own sort of tooling around what's going on in your cluster if you want to do that. But there's a lot that's not great about it, and these are some of the things that we hope get better over time. So like using Docker, like I always get the sense when I talk to people that it's like everybody's using Docker, but everybody's not happy that they're using Docker. Do people feel that way? Like Docker can be kind of a pain, especially in .NET when we have multiple projects that are dependencies of each other. There isn't really a good recipe for that. Something that myself and the rest of the ASP.NET team want to build some tooling to try and make better in the future. It's something we're thinking about. We sort of understand that the current state of things is not very good. Right? Additionally, there's a lot of concepts in Kubernetes that are probably more powerful than you need. I've shown you like really basic like day one kind of stuff so far, but there's a lot of things that you can do here that maybe aren't what you want to spend your time on as a developer. We're hoping that more stuff gets built on top of Kubernetes that's higher level in the future, that's a little bit more accessible to developers. So that's just kind of a taste of that. We're going to switch gears a little bit and talk a little bit more about writing code and about writing ASP.NET Core applications. And this is the stuff that I hope really speaks to you if you're a backend developer. Like, how do you communicate between your microservices? What protocols are you going to use? What technologies are you going to use? How do you figure out what endpoints to talk to on other services? How do you manage configuration and secrets? This is like your checklist of all your things to think about if you're planning microservices development or microservices deployment. These are all the problems that get scaled up when you have multiple apps in your system. So if you had one application in your system before, and you wanted to call from one component to another, like that was probably a method call in your code today. You might have an abstraction that you call through so that you can unit test and so that you can mock dependencies. But now that it's a different service running on a different machine, it's a distributed computing problem. How do you think about, how do I know the address of that other server? How do I know, how do I think about resiliency? Or what do I do if that other service goes down? These are not the kind of things that you had to think about when your code was all in the same process. And then lastly, when you do troubleshooting, what are your set of tools for visualizing what's going on in your topology, for tracking the performance of things, and for improving that? So I've got a sample app that we're going to look at solutions to some of these problems, and we're going to look at the current state of the world through the lens of a sort of sample or basic prototype kind of app. So what I've done is I've taken the Blazing Pizza app from our Blazor workshop, and I've broken the back end up into some microservices. So normally, the Blazing Pizza app, how it works is we've got a front-end Blazor application written in Blazor WebAssembly that runs in the browser, and we've got a sort of front-end, a back-end for the front-end app that runs as a regular ASP.NET Core Server app that's like an API server for the front-end app. What I've done is I've basically taken all the business logic functionality out of that app, and I factor that into separate concerns or separate domains. So we have a menu service which owns things like what are the set of pizza specials that are available, what toppings can you put on pizzas. We've got an order service which owns payment processing and tracking order history. And we've got a delivery service which is responsible for making the pizzas and actually tracking like where is the delivery person with your pizza, when are they going to get there. I've also, to sort of mix things up, changed some of the communication patterns here. So we're still using good old HTTP and JSON to talk from my client-side app to my front end. But we're going to use gRPC to manage most of the communications between most of the other services. And hopefully, you may have heard some things about gRPC, or you may have seen it before. I'll introduce some of those concepts and show a little bit of what that feels like to use when we start talking about the communications between those different kinds of services. And then additionally, I've got some Redis in there. I'm using Redis in this example to sort of simulate using it for like message queuing functionality, as well as pub sub functionality, as well as database-like functionality. And I like Redis from a teaching point of view because Redis is a really flexible technology and it can be used to do a variety of different things. But in practice, you could substitute Redis for like a proper message queue or like a proper pub sub functionality or like a proper database functionality. In all the cases that I'm doing here, I just wanted to do it with Redis, so I did. So with that, I'm going to flip over to my actual app, and let's run this and see it do something. And I'm done with this. So over here, I've got my Blazing Pizza app. I'm going to make that slightly bigger. And this is our pizza store from the workshop. And you can see that I've loaded in a list of pizza specials here. So this list of pizzas here and these images and these descriptions are what comes from our menu service. If I open up one of these pizzas, like I think the buffalo chicken sounds good, this list of toppings comes from our menu service as well. And I can select these. So like pepperoni sounds good. And I think I'll add lobster. And then I can add that sort of to my cart over here. Then I go to the order page, and I'm going to very carefully put in all my personal information so we can deliver this pizza. This is accurate, by the way, if you want to send me letters or mail me pizzas. When I press the Place Order button, this is actually going to submit to our order service. So we're involving our second microservice. So I'm going to go ahead and order this pizza. That's been ordered. And now the delivery service takes over. So our UI is, our backend for our front end is talking to the delivery service, and it's going to get updates from the delivery service. So the delivery service is tracking this driver now that the pizza is out for delivery, and it's going to be pushing updates out that are then going to be seen inside the browser. So we're getting updates about the status of that pizza and where it is. And to sort of visualize this a little bit differently, I'm going to use this other app here that I've written, which is a map for the managers of pizza stores. So I'm worried that my delivery drivers are like driving too fast or something like that. So I've got this app where I can just spy on them, and I'll select an order. And you can see that I'm getting pushed updates to this UI. So I'm tracking pizza order number 2, and I'm getting these like latitude and longitude coordinates sort of pushed into this app. And that's happening as this is being delivered. And then we're going to get closer and closer, and this pizza will eventually arrive. So those are some of the communication patterns that are happening inside of this app. And we're going to break those down a little bit and talk in a little bit more detail about how they work, why I made the choices I made, and what the technology looks like under the hood. So let's drop to VS Code. So I'm opening up this code right now in VS Code so we can take a look at it. The first thing that I want to point out is, remember, I've got a client-side Blazor WebAssembly app. That's blazingpizza.client that I've got right here. And I've got a server-side sort of REST API kind of app that's acting as a host for the client-side app. Why would I choose something like this, or why would I do something like this? Well, the answer is there's a couple reasons why I might do it. And this is a pretty common microservices pattern when you've got a front-end application that's a client-side application. And it's known typically as the BFF pattern, which I think of as the like best friends forever pattern, but it actually stands for backend for your front end. And the sort of idea here is that it's worth isolating your client-side application, if it's a true client-side application, from your proper backend functionality for a few reasons. First of all, you may not use the same type of auth in your front-end application as you want to use in the rest of your sort of enterprise and sort of topology. The second reason is you probably don't want a client-side application sending requests to like 20 different services to fulfill all the things that it needs. Like you sort of know the typical pattern with front-end applications where you need to talk to an API gateway or something like that that then is going to fan out and do like 2 other calls and combine the results. I don't have examples of this in my sample, but you want to try and limit the number of requests that your client-side application needs to make if you can. Having a back-end application to sort of fulfill that contract for you makes things a lot easier. So one of the things that you notice right away is I've got a few gRPC clients here, because this front-end application, or this back-end for my front-end application, is going out and fanning out into like 3 different gRPC services. So what's going on under the covers here is I have got these protobuf files, and this is part of the gRPC programming model. I've got these proto files sitting in a server in my repo, and I'm bringing them in here as gRPC services client. The reason why this is done is explained by understanding a little bit more about how gRPC works as a programming model. And if you haven't seen this before, this might look familiar to some other technologies that you've used in the past. gRPC is fundamentally a contract-first kind of programming language, or contract-first kind of messaging protocol, where you define up front in a specific format what the contract is going to be between your services. So in this case, my menu service exposes these 2 endpoints. You can get the list of pizza specials, you can get the list of toppings, and everything about the data model is described in this format that is language independent, that is like source controllable. And then what I do is, I already showed you how I import that into blazingpizza.server. My menu service also imports the same proto file, but it says that it's importing it as server because the menu service is going to act as the server for that RPC. So in my menu service, I would expect to see methods like get pizza specials and get pizza toppings. Cool. So how this works, we'll take a look at the server side first, is in startup code, you end up registering a gRPC service here. So I've got menu service impl, which I don't like impl, but the gRPC generated code already takes menu service from me, so I don't have a better idea. So I'm mapping in menu service as a gRPC service here in startup code. And then the implementation of that looks like this. It looks an awful lot like an ASP.NET Core controller. The only difference here for gRPC is some of the data types are different, and the fact that they give you a base class to generate this. The other thing that's different about doing this kind of programming with gRPC as opposed to like a REST API is gRPC is very prescriptive. So you don't see anything in these method definitions about like, I want to bind this parameter from the body, I want to bind this parameter from the query string, I want to return this status code. Like gRPC kind of does away with that level of detail and that level of customization. And it's a very prescriptive format, or a very prescriptive protocol as far as how data is communicated between clients and servers. So if you think about why would you choose something like gRPC versus why would you choose something like HTTP and JSON? Well, first of all, do you need to talk to every client in the universe? Within my microservices topology, I don't need to talk to every client in the universe. I just need to talk to my applications, right? So REST and JSON will give you probably the broadest set of compatibility for building an API, whereas gRPC is going to work really well for clients that can speak gRPC, which generally means clients that can do HTTP too. gRPC will simplify a lot of the details for you if all you want to do is do some very pragmatic communication back and forth. Now, what it looks like over here to consume this service, I can go to my toppings controller, which is where I get the list of toppings. So you can think about front-end API or front-end client-side app calls this over REST and JSON in my backend API. This thing actually kind of just proxies to the gRPC service and then does some conversions of the types of objects to give them back. So I get a menu service. In this case, I'm getting it from dependency injection right here. And then I can just call this method. So this client is code generated. I didn't have to write it. The fact that I import the proto file gives me this generated client. I can call this method, gives me strongly typed objects that are code generated to pass in the data that I need and get the data that I want back out. And that's how something like this works. So the other cool aspect of this that I can show you is I've configured something like Zipkin. I've configured distributed tracing for this repository or for my sample. So Zipkin is a distributed tracing dashboard. And in all of these applications, I have wired them up to do distributed tracing to this instance. So I'm running a service for Zipkin in my Kubernetes instance, and I have put this little bit of like telemetry code in all the services that are deployed here. What's going to happen is that all the HTTP coming into the application, all the HTTP going out of the application, as well as the Redis calls that are going out of the application, are going to go and get traced to this Zipkin instance. Additionally, if you wanted to trace your sort of arbitrary stuff, there's this activity type that you can interact with in .NET Core, and you can sort of set up your own little areas or regions of time to add to the data that's going to Zipkin. David and Damien's talk from yesterday about diagnostics included a lot of this information as well, perhaps at a little bit more level of detail. So if you want to learn more about that, I would suggest watching that when the video comes out if you didn't catch it. So what I'm going to do right now is I'm going to trace one of these calls to toppings. So I'm going to search for calls that came into the path to /toppings. I can open that here in Zipkin, and I can see that I got a request to my front end. I can see that the user agent was Mac, so it was this computer. It was the app I showed you. And then you can see that there was another call here that happened kind of overlapping in time. And this was the call to menu service get toppings. So like this URL right here, I didn't have to write that in code anywhere. It comes from gRPC. gRPC decides what that URL is. And you can see that the client was gRPC. So you can see that I've got this little like sort of waterfall chart here of what's going on in my application, what are the calls that went to various services, and what were their results, which is very valuable when something goes wrong and you want to see what happens. Let's look at something slightly more complicated, one of these more complex gRPC invocations. So I mentioned that I'm using gRPC for the order processing portion as well. So we can look at something slightly more complex here. And that would be, I happen to know what the URL is. So when I place the order, it goes to /orders. And there's more that's going on inside of here. So my front-end app makes a call to orders. Then that goes to the orders gRPC service. So you can see this is a gRPC looking kind of URL, and it's a gRPC.NET client. And then the next thing is you can see that there's some extra stuff happening here. This is the communication that's happening inside the order service with Redis. So you can see things here like what statement was being executed in Redis. Redis is kind of this like query language sort of thing. You can also see the host name of the Redis instance that I was talking to, which is an Azure hosted Redis that I provisioned, and all the events that happened as part of that communication. The other thing that's really cool about distributed tracing and why you'd like this sort of thing is you can go down here and you can get these IDs. So these IDs are the things that make distributed tracing work. And they flow around in headers on all the communication that's happening inside your microservices app. So ASP.NET Core, this is a standard, by the way. We didn't invent it. We did invent our own thing, but this is a standard version of it. This is a standard called OpenTelemetry that Google and us Microsoft, and a couple other companies are investing in. And it's basically agreement on what these header names are and what the values look like and what the semantics of them are, so that no matter what kind of programming stack you're using, you can have these similar kinds of experiences. Now, the part that's in .NET Core is the fact that when a request comes in and it's stamped with one of these headers, we will do the right thing for you inside .NET Core to wire that up to propagate those. So it means that here I have a trace ID and I have a span ID on my incoming request from the browser. In my call to gRPC, I've also got a span ID and a parent span ID, because we've propagated that information from the original call, and that's what powers this, this sort of diagram, is the relationships between these traces, as well as the information about when they start and when they stop. Let's look at a slightly more advanced gRPC example that I've done here, which is that my delivery service is able to push updates, and we're able to receive updates. And I want to go to my manager app, which is my little spy app here, and look at the data of how this is powered. So this is a Blazor server app, which is why it's able to react in real time like this. And the really important sort of money part of this is this onSelected order change. So when I selected in that dropdown, I want to monitor order number 2. This is the code that ran. So again, I've got a gRPC client. I go to track the delivery. I pass in the user ID and the order ID I'm interested in. And then I get a response from the delivery server. But instead of a single response, I get a streaming response. And I can call read all async on that, which gives me back a C#8 async awaitable, or async enumerable. And I have something that I can then async for each, or await for each, and get each message as it comes back. So that's how I'm able to like stream those status messages in. It's coming back asynchronously as the server pushes them to me. We call this in gRPC server push. If I wanted to see how that's implemented, I can go into this gRPC application and take a look. So in the delivery service application, I've got this gRPC service, the delivery service, and it's got 2 endpoints. It's got delivery status, which returns a single status, and it's got track delivery, which is what returns a stream of these delivery statuses. And inside here, I'm not going to explain this code in super detail, but you can look at the sample if you want. I'm basically listening to a Redis pub sub, and every time I get a message on that Redis topic, I'm going to fetch the current state of where that driver is, and the current status of that pizza delivery, and I'm going to push it out over that gRPC connection if anybody's listening to me. So this is like a flexible way to have people subscribe when they want notifications. They can hang up when they don't want them anymore, and the server just gives you continual updates of what the status of that pizza is. So how these things are produced, we're going to talk a little bit about Redis now. Inside my delivery service, I've got a couple things happening. So I mentioned I've got this gRPC service here, and I've also got this hosted service. So hosted service in ASP.NET Core is typically going to derive from the background service class. And if you haven't seen these before, you probably have written something like this or have wanted something like this in the past, and you might not know that we already have it. So definitely check that out. Background service is the thing that you want to reach for if you want some job running in your process, in your service, that is going to have the same lifetime as the service, but is not going to handle any requests. So in this case, my background service awaits, and it basically just subscribes to a message queue. In this case, I'm subscribing to the orders message queue. So this GUI here is kind of how you do message queues in Redis. I'm listening to a topic, I'm looking at a list and saying, are there any orders that need to be processed? And then I'm listening on a topic to get notified when that list is updated so that I can check again, basically. So I'm pulling orders off of this message queue, and then every time I get an order, I'm going to process it. And you've now reached the point where the veil just completely shatters on my demo. So there's no actual pizza store anywhere here. I know, you're shocked, right? There's no actual delivery person that's bringing these pizzas anywhere. It's all simulated. This is the code that simulates that pizza delivery, and this is the code that pushes those updates out. So we pick a timer of a minute, and we interpolate from wherever we said the pizza store was to where we're saying that the person is, and push out updates like every 3 seconds or every 5 seconds with the driver's new position of just them moving closer and closer until it's delivered. So we totally fake the pizza status thing. So something you might be asking yourself at this point would be, why am I using Redis to do this communication inside of a single process? Because I said that the gRPC service for delivery and the Redis service for processing orders and pushing out status updates are actually in the same service. And the reason is because of statefulness and because of scaling. So My microservice here is stateful because if somebody subscribes to get updates for an order, they want to get updates for that order no matter where that order is being processed. But since I'm reading the orders from a message queue, only one app at a time is processing those updates. So the fact that I can put something like a Redis in between means that no matter how many instances I have of my delivery service, anybody can subscribe to notifications for any order on any delivery service. They don't have to guess which delivery service is the one that processed that order. The updates flow to everybody. Could I have made these two services? I probably could have made them two services. So there's all these technologies that we're using here and all these different ways that we're sort of interconnecting and talking to different services, but we haven't talked about solving any of the questions of how you find them or how you talk to them. Well, Kubernetes has kind of got your back for this. There's a couple things that Kubernetes does that can really simplify your life when it comes to microservices communication and how you find other services. So the dumbest thing you could do is you could do this. So I'm going to make this slightly bigger so you can see. And I'm going to say kube control get service. This is listing for me all the services when it decides to. This is going to list for me all the services that are running in this namespace in my cluster. And you can see I've got some of my app's services here, delivery, front-end manager, menu orders, those are all the things I mentioned, as well as stuff that's infrastructure like Prometheus, which I'll talk about in a little bit. And you can see for some of these, for all of these I have a cluster IP, and for some of them I have an external IP. So I've got an address that I can use to communicate with this service inside the cluster, and then I've got an external load balancer address that I can use to talk to outside the cluster. Well, these service names are actually just host names. So for instance, if I'm inside the delivery service and I wanted to talk to the front-end service or talk to the menu service, I could literally just HTTP menu, and that would work just fine. So kind of like the dumbest thing you can do if you're on Kubernetes is you can just use DNS, because Kubernetes uses all those features. So Kubernetes will create DNS records for all your services. You don't actually need to know how to find them. The logical name that you gave to the service is the host name, is the address. What if you wanted to do something else? So let me show you something that I like to do when I write this kind of application. I like to basically make these things work, but make them work with a default. So in my startup code here, I've got this little helper, configuration.getServiceHostName, and I'm passing in what I want the defaults of these host names to be. So for the delivery service, I'm going to hard code and assume that if nobody's told me otherwise, I can talk to it on delivery. Likewise for menu and orders. If nobody's told me otherwise, I'm going to assume that the logical name of the service is the host name. The nice thing about that assumption is that that will work really well if you're on Kubernetes and you have a simple configuration. It will also work really well if you're running locally with something like Docker Compose and other things that are multi-host container kinds of systems that provide DNS and networking services, which would be all of them. This kind of really simple scheme is supported by a bunch of different stuff. If I wanted to get more complex with it, let's look at what this code does. So this code is going to use the iConfiguration object that you get in ASP.NET Core, and I've got a simple convention around what keys I use. So I take the logical name of the service, and so I'm looking for a key service, and then the service name. And whatever is there, I'm going to assume is supposed to be the URL of this key. What I like about this design and what I like about doing things like this is, first of all, I can provide a default, so I don't have to set this everywhere because it would be kind of a pain. Second of all, if you don't have the information you need, fail hard, fail very clearly with a clear error message. So if I don't have a reasonable default and I didn't provide a configuration value, this service will fail to start. If you have messed up the configuration of something, it will fail in a very clear way with a very clear error message so that you know what the problem is and you're not hunting around with a bad error message or a timeout or something like that. Failing fast and failing loudly can really help you. If you wanted to, you could go even further, or you could say something like, I'm going to have a health check that looks to say, can I at least ping that thing? Or can I at least verify that I've got configuration? There's a couple different ways to fail. What this would look like to actually configure it, the sort of simplest thing to do is, well, you could use an environment variable. So in ASP.NET Core, if I wanted to override this, I could provide a value for this with the environment variable, let's say for the order service, like service underscore underscore orders. It's not a mistake, it's 2 underscores. It's supposed to be 2 underscores. 2 underscores, we let you use 1 underscore for readability in environment variable names in config. 2 underscores in ASP.NET Core means this is a separator. So it's effectively replaced with a colon. If I were using JSON configuration or something like that instead, if I were using JSON configuration or something like that instead, then I would make an object service and then orders and so on. So you get the idea. So we have a hierarchical configuration system. It has a variety of sources. It will give you a little starter JSON file in every project by default. When you're thinking about microservices and deploying to the cloud, you really end up first thinking about things like environment variables as sort of like the easiest thing to do, because environment variables are very foolproof and they're very easy to troubleshoot because they're very easy to inspect with like any sort of tool. But where you probably don't want to use environment variables is you probably don't want to use environment variables for your secret data. The reason we don't like environment variables for secret data is that they're kind of inspectable by like anyone. So if you have access to the machine or you have access to look in the like Kubernetes UI to find out what's going on with a pod, then like chances are you can see the environment variables of that and you can see whatever data is in there in just sort of plain text. So like we don't want to use environment variables for secrets. What do we want to do instead? Well, the answer is that we can still just use configuration. Because in ASP.NET Core, your secrets come in through configuration anyway. That's how things like Secret Manager or Key Vault work in Azure. Things get mapped in through your configuration system. The configuration system is how we read those things. But how would we get a value into our service in the first place? So in my order service, I need to talk to Redis. I also do this in the delivery service. And the way that I can get this secret in here is I've defined a secret already in Kubernetes. So I use the Kubernetes command line to define a secret for my Redis. I basically went to Azure, provisioned a Redis instance, and then I went to Kubernetes, and I put that connection string in a Kubernetes secret using the command line. Since I'm on Azure, if I had wanted to, I could use Key Vault and import a Key Vault into Kubernetes. You could do the same thing on other cloud providers as well. It's kind of a standard integration that they all provide. But I just did a normal vanilla secret. And the way that I do this is I can take this secret and I can map it to a file. And that file name is the service underscore underscore Redis that we talked about. So basically, by mapping that secret to a file with a name that matches the configuration key that I wanted to use, I can easily get it inside my app. The app code, what the app code looks like for that is inside my program CS, I've added a configuration store. So this path matches what I put in that Kubernetes manifest. It's going to find files in this directory, and it's going to map the contents of each of those files in as a configuration value. So it's going to take the file name as the key and the value that's in the file as the value. This configuration source has got a pretty bad name. It should probably just say add Kubernetes configuration because this was written specifically for Kubernetes' configuration system. But there you go anyway. So on the monitoring front, on the sort of diagnostics and monitoring front, there's a couple things to say about this. One of the things to say about this is logging and logging dashboards. ASP.NET Core has got what we call a structured logging system, where we log not only a textual message, but we also log key value pairs. When you're running in these cloud sort of environments, what the standard thing to do is to use like a JSON formatted logger. You can use Serilog for this, which is really good. I don't have that set up here, and I'm not going to show a logging dashboard as part of this demo, but the information is out there that's available if you want it. One of the really cool things that you can do with that, which Damien and David showed in their diagnostics talk, is you can take those trace IDs from Zipkin, you can go to your logging dashboard, and you can put that into a query, and then you can see all the logs from all the services that executed on that trace. These are the kinds of things that you'll find pretty essential when you're debugging and building applications like this, is you want to set yourself up for success with easy ways to see all the diagnostics across all your different apps. I did mention Zipkin already, which is I'm hooking up Zipkin here via the OpenTelemetry package. The other piece of magic that I have got here is I'm tracking metrics from these applications. So I'm using a package called Prometheus.net, which is a lovely community package that someone has made. And I've got this middleware here that's tracking HTTP metrics. This sits in between routing and endpoints. And the reason why it sits in between routing and endpoints is it's going to capture the results of routing. So it's going to look at what routing decisions were made, and it's going to incorporate that data into the telemetry kind of information that it logs. And then this endpoint down here is going to expose an endpoint on the /metrics URL. So one of the things that I've done with all of these services that you might want to think about is I've configured for all of these apps, I'm basically listening on both 80 and 8080. And the reason why I'm doing that is I'm directing all of my diagnostics-related tracing or all of my diagnostics-related traffic to 8080. The reason why I might care about that is that things like metrics monitoring systems and health monitoring systems typically don't play super well with your various different kinds of authentication. They may not play well with HTTP2. They may not always play well with TLS, depending on what the system is. And it's nice to be able to separate your applications like production traffic from your diagnostics only traffic. One of the new features that we added in routing in 3.0 that I'm pretty happy with is you have the ability to filter on endpoints. Filter endpoints on port or filter endpoints on hostname and things like that. So one of the things you might think about as you're building applications is like, well, should we listen on a separate port for our diagnostics traffic? And should we filter that port out so that those things are not accessible over a normal sort of connection to our public endpoint? So like in this case, if I wanted to, for this metrics endpoint, for this health checks endpoint, like I could require some type of authorization if I wanted to. I could filter by host. I could implement various other policies that sort of filter what traffic can go where in my application. The routing system is extensible to do all those things, and you'll find a couple of them built in by default. So the reason why I have these metrics endpoints exposed is I'm using something called Prometheus in this cluster. What I'm showing you right here is Grafana, which is a popular metrics sort of visualization tool for Prometheus. And the way that this sort of works speaks to the power and the flexibility of Kubernetes. There's a daemon or a sort of worker running in my cluster, or a set of workers running in my cluster that are going to go to all my services and hit that metrics endpoint at intervals. I think it does like every 30 seconds by default. And it's going to basically ask that endpoint, what data do you have that you want to share with me that I will then take and use? There's also a bunch of metrics gathering information that you get from Kubernetes by default when you install something like Prometheus in it. So like I've thrown Prometheus on this cluster, and I can see here for the Blazing Pizza namespace where my app is deployed, what's the CPU usage in a stack chart format of all the different apps that are running here. And you can see that there's a little bump in activity when we were actually using my app from a couple of minutes ago, at about 10:45 when I really got into demoing stuff. And then after that, it's been pretty quiet because we're just sitting here. It's a little early for pizza. Likewise, you can look at things like CPU requests and quotas. If I had assigned requests and quotas, which I'll explain in a minute to my apps, how am I doing against those quotas? Am I using all the resources that I allocated for these pods, or am I not? Likewise, you get things like memory usage and network traffic and things like that. And you can get a lot of this stuff for free without even doing anything to your apps, because when you install Prometheus in a cluster, you're going to get a lot of these things for free. Now, the major cloud providers all have similar kind of offerings for this. I know Azure's is called Azure Monitor. Other cloud providers have similar offerings to this. I'm showing Prometheus today instead of showing like Azure Monitor, A, to avoid leaking any of my Azure credentials to you, and B, to give a sort of cloud provider neutral view of what's possible. The Kubernetes and Grafana stuff is really probably best of breed. All the cloud providers have something similar, but that might not be as powerful, but it also might be set up for you a little bit easier out of the box since it's just going to come with your Kubernetes instance. The other thing that I've done here that I want to show you is I have written my own dashboard using the metrics that are exposed by my apps. And these are coming from that metrics endpoint that I exposed in my apps. Now, I'm a total, Prometheus has its own like graphing and query language that's fairly complex, and I'm a total newbie at this. I'm actually proud of what I was able to accomplish. I've got a little graph here that shows the requests, the number of requests coming into the app, as well as the number of failed requests coming to the app. So I can pick in this picker which of my apps is running, and how many requests are coming in within a given period of time, and how many of those were failures or non-200s within that same period of time. The reason why there's some baseline level of traffic to all these apps, despite the fact that we're not actually using them for anything, is because I've got those health checks running. So Kubernetes is poking all my apps and being like, hey, you all right? You all right? You all right? The other thing I want to mention about this is that this is data-driven. So like, I didn't actually have to write down anywhere what are the names of all the apps that you want to monitor. And I also didn't have to write down what are the names of all the apps that you want to show up in the monitoring dashboard as options. So hopefully this gives you an idea of some of the kinds of things that you can get for performance monitoring and for troubleshooting and for examining and diagnosing problems. I think that the kinds of performance-oriented things that Prometheus can show you and other cloud-based solutions can show you, probably more advanced than what most of us use on a day-to-day basis. And there's really a lot of mileage to get out of these kinds of systems without spending a lot of time setting them up. So with that, I alluded to earlier something called requests and limits for containers. So part of Kubernetes is the fact that Kubernetes decides where your apps run, right? So when I said I want to have 3 copies of this app, I didn't have to say I want 1 on each machine or anything like that. Kubernetes actually allocates your apps where it thinks is best. You have some ways to influence that and some ways to control it. But one of the rules that matters the most is you can tell Kubernetes how much resources a given app wants, and it will put it where it thinks is best, or put it where it thinks it can accommodate your expectations for amount of resources for that app, which is pretty cool. But I think as well as .NET developers, we're like a little bit in the dark about this. Like, what does it even mean to figure out what kind of resources your app will need? Like, how would you even go if I told you, you're going to start using Kubernetes and you're going to start needing to understand the resource requirements of all your apps, where would you start today? And the answer is, I think a lot of us would draw a big blank. Like, how would I even figure that out? So I've done an experiment. I wanted to basically do some of my own performance testing around this. We know that ASP.NET Core and .NET Core can perform really well when we're talking about high throughput with lots of traffic and access to lots of hardware. See the Tech Empower benchmarks if you don't know what I'm talking about. We've got industry-leading performance for HTTP in terms of frameworks and tools and technologies you'd actually want to use. But how do we do when you're thinking about things that have to scale down really small? Like, how do we do when you've got a really small amount of resources? This comes up a lot when you've got, I've got a bunch of apps that I need to run. They're separate because that's the way I wanted to architect it, but some of these are really low traffic. Like, I don't need to send a lot of data from them. I don't need to receive a lot of data from them. How would they do with low resources? Or if you want to write the kind of infrastructure that runs in Kubernetes, some of the things that Kubernetes provides you that run inside the cluster itself are allocated like 50 megs of memory and like 1/10 of a CPU core. So let's take a look at that. This is what it looks like, by the way. I'm going to speed up a little bit because we're almost out of time here. This is what it looks like to actually define requests and limits for one of your containers or one of your pods. This is something you will have to do if you want to use auto-scaling. So Kubernetes has the ability to do auto-scaling based on load. You can't do that unless you define what you think normal looks like for an application. The experiment that I did is I wrote the same app in a bunch of different tech stacks. So Go, Python, Java, .NET, the kinds of things that people think about writing cloud and microservices types of applications. And I measured those with fixed amounts of requests per second. And I varied the amount of CPU and memory allocated to them using Docker. So our test environment has the ability to run Docker. We have a pretty robust benchmarking setup in the office. And I'm able to simulate a Kubernetes kind of environment by just using Docker. And then I'm measuring latency, working set, CPU usage, and the percentage of traffic actually served. The reason why that last one is there is if I asked for 100 requests per second and you gave me 50, like 50% is an F, like you fail, right? So we want to know what percentage of the traffic they were expected to serve that they actually served. And the intent here is to simulate what it's like for a small microservices app getting a predictable amount of traffic. So the experiment has, you have incoming HTTP, incoming JSON serialization, outgoing HTTP, outgoing JSON serialization, and most importantly, calling some other service that has some amount of delay. So if it were instantaneous, it's kind of artificial. What do our microservices apps do? Well, we looked at that in Zipkin, right? They call other services. So I wanted to include calling another service as part of this. I wanted to see how ASP.NET Core would stack up here. For that reason, I'm kind of redacting the names of the other tech stacks here. If you're really curious to know the results, come and talk to me afterwards, and I'll talk to you if you promise to be mature about it. I did not want to get on stage and give a presentation where I talk down to Java users or Go users or anyone else like that, because that's not very nice. I wouldn't like that if somebody did it about .NET. Also, not every technology claims to be good at what I'm doing. So is it a little bit unfair to throw some of the Java frameworks into this kind of testing? Maybe. I think the people that make those frameworks might say you wouldn't be successful with this, and it'd be unfair to call them out for something that they say won't work. So let me unpack what you're looking at here. So we've got our sort of combinations across the bottom. There's 30 megs times a quarter of a CPU on the small end, 360 megs of memory and a full CPU on the right end. Something that very smart people get confused about when they see this, and you're even smarter so you won't get confused. One CPU does not mean one core. It means one unit of CPU. So it's not, one CPU does not mean you're single threaded. It means that if the machine has 12 cores, you get 1/12 of the machine, if that makes sense. You can run things in parallel with one CPU because it does not mean one core. It means, in my 12-core CPU case, 1/12 of the machine's processing power aggregated over time. And you'll see that on the small end, so talking about this data, you'll see that on the small end, there's some things that don't appear. So this yellow bar, this gray bar, and this sort of brownish bar don't run. They don't serve 1 RPS at the smallest amount of resources that I tested, but a lot of them do, right? And it's only when we get into the like 0.5 CPU times 100 megabyte category that stuff show up. That all the workloads show up as working. One of them's got really high latency. I'm using latency in these charts as sort of a measure of health. 10 milliseconds is the theoretical minimum for latency in this test. So if you're around 10 milliseconds, you're healthy. If you're much higher than that, you're not keeping up. Likewise, let's bump it up to 100. And we can see that some of these stacks start to struggle. We can see that whoever's in green is starting to have a hard time at 100. Whoever's in gray is having a little bit of trouble at the smallest amount of numbers and doing well at higher numbers. Cool, let's bump it up to 1,000. Whoa, you can see that a lot of stuff dropped out, right? So a lot of our stacks dropped out. A lot of them are not able to do it at the smallest amount of requests. Let's bump it up to 10,000. Ooh, so we've reached a limit here where at these very small configurations, not everybody's able to serve 10,000 requests per second, which is kind of a high number for a really small amount of resources. But some of them are able to do it with more of the resources that we've allocated. So think about this 100 RPS or 1,000 RPS slide, and think about which ones of these you think are .NET Core, because I'm about to reveal to you. So this is the 1,000 RPS slide. Blue is .NET Core with ASP.NET MVC controllers. Pink is .NET Core using routing and JSON and HTTP client without MVC. So if we look back at these slides and sort of analyze this, like, we're doing really well in all of these configurations at 1 request per second. We're doing really well in all these configurations at 100 requests per second. So if you had asked me before I did this kind of testing, can I write an ASP.NET Core app that's going to run and run well with 30 megabytes of memory and a quarter of CPU time? I would have told you no. I was really surprised by that. So it's doing pretty well. It's not all good news. I think some of the bad news here is, well, these benchmarks were written by a framework architect, and they were written kind of carefully. So like, it's clear that MVC is not a great fit for all of these kinds of scenarios. You can't take an MVC app and give it 30 megabytes of memory and scale it up to crazy amounts. I think we want to work on closing that gap, but if you have scenarios like this where you want to write a really small app that does a lot of stuff, think about dropping the level of abstraction. Think about going to lower level concepts to get more performance out. I'm going to speed through a couple other things because we are over time. So this is a heat map. This shows basically success. So think about more resources as you go from left to right, more RPS as you go from top to bottom. Green means good, red means bad. This top left one and bottom center one are the two ASP.NET ones. So route to code is the bottom middle one. So again, it is actually surprisingly good. You've got a lot of options and you've got a lot of flexibility if you're in one of these scenarios where you really want to run with density. This is what I'm talking about with route to code, using routing at a low level of abstraction. We're going to make a bunch of improvements to this. In 5.0, doing this sort of thing is going to be a lot simpler. We're taking the JSON stuff, making the performant thing be the easiest thing to find. All right, and that's the end. Thank you all for being a good audience. Enjoy the rest of the day.